that which motivates most of our discussion today and from last time was, where else can we live in this big night sky, right? And of course, the biggest and best strategy for figuring out where to live is maybe find somebody else living there. Not necessarily the big green man, but the little green man, the little bacteria. Where can we see signs of life? And so I want to take a little bit more time to explore that idea because I think that it's going to be increasingly important. It's a very long-term project. This is not, moving to another world and colonizing it. It's kind of a bad word to use. I don't know a better word to use, though, right? Let's say finding somewhere to camp out at across somewhere outside, maybe in our solar system, but probably not. That's going to take multiple generations to achieve. But I think that the project of looking for life is the very earliest seeds of that. Because if you can find somewhere that has plants, maybe has photosynthesizing bacteria, well, there's a good chance it has everything we need there too, right? We can't live without the plants in some sense, and so that's a really good place to start looking. So how do you find some place that has life? We cracked this open a little bit last time, but NASA started looking for other planets, first of all, which is a good place to start. You're probably not going to want to live on a star, and so we have to narrow it down. So they've started looking for these exoplanets, and they've started more recently looking in our immediate neighborhood as opposed to looking really far away. Does anybody remember how they find those exoplanets for the most part? Yeah.
Wasn't it looking at the shadows?
Exactly, yeah. So they look for the shadows. They look for, and then they try to narrow that down because, dust and other things can create shadows too. So they look for this regular orbital periodicity of those shadows. And they do these light curves. And then once you find some planets, how do you figure out if it's one that we want to live on? In some sense, we just talked briefly at the end of last class, I'll go back to that slide, about this circumstellar habitable zone, right? There's a place where planets are getting enough light to cook their surface enough, if it's a water world, which it turns out a lot of them turn out to be water worlds, that's good news, but not a lot of them are in this perfect Goldilocks zone where they have liquid water on the surface. You get too close, the water is getting cooked off, it's vaporized, right? You get too far away and it's ice, and there's a really, really narrow band, which I'm sure everyone can appreciate. I mean, I don't know if any of you have worked in an office with like a thermostat or something, and you have to share that with other people. I mean, people will fight, have fist fights over 2 degrees of temperature change, right? We're only comfortable in a really, really narrow zone of temperature. Biology is kind of like that. And, you'll die if you go outside in the winter without a coat on for too long, right? Or in the summer, right? You'll dehydrate. Your water will evaporate out of your body. So we need this really narrow zone in order to circumscribe our potential habitable regions. And so that's one of the first things that we do is we look for where these planets are occurring at. Now, that's almost about as far as we've gotten with this project. And so what I want to move into today is where do we go with it next, which is what other signatures can we hope to find from these planets. So let's say we make a nice list of planets that we see, exoplanets and other solar systems. We find a list of them that are in this nice Goldilocks zone. Now what do we do? How do we narrow it down even further? And so there's a few strategies for that, and I want to play with them today. Honestly, in this lecture, we're supposed to get into start talking about the moon and Mercury. I don't know that we will, but maybe. So if we get through this, we'll talk about that. We have to talk about water in order to make this discussion possible. And I guess I haven't impressed upon you, I've impressed upon you perhaps that there's a climate zone, there's a temperature region that's really important. But why water? Why do we care about water? Well, just from an empirical standpoint, obviously we all like to drink water. Everything seems to use water in some sense, all the living beings on our planet. But occasionally you'll encounter these arguments like, well, maybe there's silicon-based life forms or other carbon-based life forms that aren't necessarily requiring water. And I'm very skeptical of that because I think water is, in some sense, an extremely unique chemical. And so I want to talk a bit about why water is so special, because it might not be entirely apparent to you. So water's really, really amazing and unique among chemicals, or among molecules, in that it has the ability to possess two charged surfaces which are opposite at the same time. We haven't really rationalized what the word charge means, and that's a little bit of a disaster to open that can of worms at this point. But, in general, we talked about the surface of atoms, and the surface of atoms do something which they do it onto one another, which results in the production of electric currents, right? There's something that the surface, the electron shell of atoms is actually doing physically to another atom, which results in the propagation of that motion down the chain of atoms, okay? I think that a good way to think about charge is sort of like the directionality of that motion. So if one atom is, say, twisting another atom that's in the next one in the chain to produce current, it's twisting it with a certain handedness. We can think of it that way. For instance, you can think about a hurricane might rotate one way or the other, depending on which side of the equator it's on. We don't have to get into why that is, but I think there's something similar going on with charge, and that's probably a good way to think about it, is the handedness of that motion. And so water has an oxygen. It has two hydrogens stuck on it. The hydrogen's outer surface appears to be rotating in a different way than the oxygen's outer surface, and so it has two interactions possible. It can really sync up in two different ways. And on its face, that seems like, okay, that's kind of a cool parlor trick. But what that allows it to do is it means that water can interact with itself, and it can bind to itself, and it can make little structures all by itself. I mean, the easiest one of these to understand is ice, right? Ice has a really perfect little crystalline lattice structure. And, this is very difficult to achieve, this kind of stiffness and rigidity and utility of ice with other compounds that aren't polar. They call it polar, right? Because it has two poles. It has this positive surface and this negative surface. So water can organize, and what you know about ice, but what you don't realize is that water actually does this even in the liquid form. So there's transient lattice structures, there's transient versions of these architectures that can appear in water, right? You can actually get these, if you look at, they do this really cool experiment, this thing called an atomic force microscope, which is basically this tiny little cantilever that can, you shine a laser off the back of this flexible cantilever, and you can see tiny little deformation, like as it bends a little bit, you can see that. And what they can do is they can do cross sections of water, and what you can see is that as you move away from the surface, where the water is filling a container, let's say, you see the individual layers of water structured into sheets upon one another, right? So it's not just this chaotic liquid. There's actually these transient structures. And what I mean by transient is that it's not like an individual water molecule stays in place like it would in ice. What it does is the water molecules individually can swap out in the structure, but the structure persists nonetheless. And so water can make these incredible structured architectures within itself. It allows it to perform tension. It can pull on other molecules. And so as a result of this, what's really incredible is that water can do a lot of work inside of the cells, right? It can actually, one way to think about biology is the way that you probably learned in high school, which is like, DNA leads to RNA, leads to proteins. The proteins are essentially form your cells, and they do all of this work. They catalyze reactions and stuff. But I think an equally valid way to look at it is that the water molecules are organizing the proteins to do all of the work that they do. Because in reality, 99 out of 100 molecules in your body are water, right? So most of the molecules are water, not by mass, but just by molecule count. So those waters are all organized really, really nicely with one another, and they form these tensile structures. you can really, really feel the tensile property of water if you try to like jump off of the high dive and you don't, land properly, right? The surface is extraordinarily tense, and the reason it can do that is because of this ability to structure with itself, to pull on one another at these two different interfaces, the positive and negative regions of it. So it's pretty cool stuff, and I don't know that there's anything else that we're aware of in nature that's able to pull this off. Another thing that it can do, which is probably the other amazing part, is that it acts as a universal solvent, right? It can actually pull apart salts, right? Because salts like sodium chloride, right? That's probably the favorite one in America. Sodium chloride is also a positive ion and a negative ion. Well, because water has the ability to surround each one of those with either its negative end or its positive end, it can dissolve salts really easily, right? It can actually dissolve most things really easily, it turns out. The only thing it has a hard time with is nonpolar entities. And that's why when it comes to like industrial production of, plastics and so forth, those things are often nonpolar, and they require nonpolar solvents, which turn out to be really toxic, nasty stuff, benzenes and things like that. So water is a fantastic universal solvent. It's also really important for plants too. So it's easy for us to understand how water matters to us. But does anybody have a sense of how plants use water? Yeah?
Helps with photosynthesis. It's like a vehicle, and it's also how they deliver oxygen to the root.
Yeah. So do you have an idea of like how the water gets up into the tree? It's kind of incredible, actually. So, this idea that water can attach to itself and exert extraordinary tension upon itself is at the heart of why plants, you look at a redwood tree and you're like, how the heck does it pump the water up into the, hundreds of feet off the ground to the leaves, essentially? Well, it's really, really incredible how it does that. Actually, what it does is at the leaves, what's happening is you have evaporation, right? They're these big open evaporators, essentially. And there's all these little holes there. And those holes are in some sense connected to the water column inside of the plant, inside of the body of it. And what's happening is that as the individual water molecules get kicked off and evaporate from the surface of the leaves, they actually pull on the waters below them just a little bit. And in aggregate, all of those pullings pull all of the water all the way up from the roots. So it's this tensile process. It's really, you can think of it like you're pulling on a cable, and it's these big cables of water that are getting yanked up to the surface. And this process is called transpiration. So without that cohesive ability, I don't think plants would work. It's hard to imagine a plant that would work. What else can we say? Cohesion also helps with maintaining water's really high boiling point. Because if you think about what's happening when something boils, right? It's basically an accelerated evaporation. But in order to have something boil or evaporate, you have to have those individuals pop off of the whole, right? And the fact that it has so much cohesion means that it's really pretty hard to boil water. And that's good because it means that we retain our water pretty decently, right? If water's boiling point was much lower, well, you would evaporate very quickly, and it would be lights out. So that's pretty amazing too. What else do I want to say about water? I think you kind of get the points. All right. What's really interesting, though, is that there's surprisingly not too much of it on Earth compared to the rest of the stuff, the rest of the rocks that we have, right? So this is all of the water, if you could imagine it in a droplet next to the Earth. That's the moon over there, right? So it's a bit smaller than the moon. And I'm sorry, that's actually that's not our moon. That's Europa. So we can't be losing this stuff, right? And I think that's a lot of the that's a lot of the worry about with respect to climate change too. In some senses, is that this is a delicate balance, and our whole lives depend on water. And of course, the water can become bound up in the ice caps. It can end up in the atmosphere, and it's a really fine-tuned balance that we need to maintain. Let's take a look at how much water is on some of these other planets. I think this is why Europa is so attractive in some sense, and we'll talk about Europa in depth later, which is one of these outer moons beyond the asteroid belt. But in terms of our own solar system, when we're thinking about where might we be able to spy some life at, these are the candidates. And the cool thing about those planets, too, what they're realizing is that, they're not planets, I guess, they're moons. What makes them really interesting is that they have these icy shells, but there's some evidence that there's actually liquid water below those shells. In some sense, in some cases, there's actually geysers that we can see. Here's a picture of one of them, actually. This is a geyser on Enceladus, which is one of those moons on Saturn. You can see the sprays of liquid water that are being jettisoned out from the cracks in the icy shell. And so there's some hope that some of these bodies may actually harbor the conditions. At least if they have liquid water, that's a good start. It's also potentially a good start for us setting up let's say waypoints on the way to exploring other places, because water is at the heart of our fuel sources too. We can make rocket fuel if we have water. And there's a little bit of water on the moon. We think it's down at the southern pole. So if we get around to talking about the moon and the exploration of the moon today, we'll see that our end game, our goal, is to make our way down and figure out a way to actually harness that water and make something approximating, let's say, a moon base where we can refine fuel and maybe launch other projects from, because it's a lot easier and cheaper to do it there. Mars also has a little bit of water. They think that there's a subglacial lake at the southern polar ice cap, which is interesting. But Mars has other problems. I don't think that we're going to be very happy there. It doesn't have a magnetic field. We'll do more time on Mars next week, but it's pretty dangerous to hang out on a planet without a magnetic field, right? You're subject to all of the radiation, all of the sun's high energy atoms and so forth. Okay. Now, there's this concept we need to bring in too, which is called tidal flexing. So why does Europa or Enceladus, why do they think that why are they able to maintain liquid water when it's so darn cold out there? And the basic idea is that these things are in orbit around these giant bodies, like way, way, way bigger than Earth. And as they get yanked around it, there's a sort of sloshing of their interiors as they do it. That sloshing creates a lot of friction, and that friction is actually sufficient enough to warm up some of the water below the surface. So tidal flexing seems to be the mechanism that allows for subsurface oceans. And so actually a lot of these exoplanets that we see are, of course, the easiest ones to see are the big ones, right? So we are able to, a lot of them happen to be these giants, what would have been formerly called gas giants, but they're more like liquid giants. But they probably have moons also that might be similar to these ones in our solar system. So even if the ones in our system are a bust, we might have a chance at setting up shop on one of these other moons, which would be really interesting to live on a place that was orbiting another planet. Very foreign. Okay, Enceladus. We'll talk more about Enceladus soon. All right, so let's say that we find some planets that have liquid water. We find, and of course we know water is extremely important. It's a basic requirement for life. What else can we look for? That's the next question. When Anastasia was talking about the origins of life, she mentioned that there were speculated to have been bombardment by these chondritic meteors that carried all of the nice things that we need. And some of those nice things were things like lipids, carbohydrates, nucleic acids, amino acids, the things that are essentially the little building blocks of an organism that essentially just need to be organized and patterned by nature. And so the mechanisms all for origins of life kind of all start assuming that these basic ingredients are present to begin with. And so it makes a lot of sense that we should go looking for those ingredients, right? And we have some ways to do that. So we're going to try to find those kind of lipids that make up the cells, the membranes of cells. And there's some different techniques we have for doing that. It turns out that you can actually use the light signals from these planets to glean some information about what potential molecules are present. One of the more interesting ways of doing that is that all of the molecules in your body have a particular handedness to them. So you can imagine, here's an amino acid, let's say. There's a mirror image of it, right? This, any particular molecule could be formed in one way, and you could imagine reconstructing it in a different way that was just the mirror image of that molecule, right? So whatever atoms are stuck on the right-hand side will be stuck on the left-hand side, and so forth. What's really interesting is that all of the amino acids on our bodies, all the ones in our bodies and all the ones in all the bodies everywhere on Earth happen to be this right-handed form. Now, what's really cool about that is that that's a really interesting signature of life right away, right? For whatever reason, we've evolved to only use these right-handed molecules, although the other ones do naturally occur. So what you can do is you can actually see whether a molecule is right or left-handed by the way that it scatters light, essentially. And so if any of you guys have taken any basic, well, you probably haven't, but if you do like intro chemistry labs or even some intro biology labs here, they have these very basic machines that are able to detect the handedness of the light as it gets scattered, right? And so this is actually a pretty easy thing to do. There's something called polarization of light, which, I don't know, well, let's just, I think we talked a little bit about light in maybe the second week, and we talked about light as being this, it's very easy to imagine light as an antenna process where even individual atoms act as little antennas that relay light signals. And when they do that, when an antenna relays a light signal, it has an orientation to it, right? You've seen antennas, on like these giant rigs or something. They have an orientation, right? And in reality, there's this propagation of current through that antenna, and it's going back and forth. The polarity is changing at all times. But you can imagine that the polarity is changing like this, back, let's say horizontally. It could also be changing like this, vertically. And so these different polarizations can precess, right? You can imagine that the polarization is doing a kind of, like, I don't know, a tilty type thing, right? And you can see that in the light signal that's coming. It's called the polarization of the light. And so we can actually, from the polarization of the light that we get from these different planets as they pass through the shadow, as they make a shadow across these stars, you can see the atmosphere giving some polarized light that gives us information about the handedness of the light, the handedness of the molecules in it as it's coming towards us. So this is pretty cool. This is like a brand new, well, not brand new, but this is kind of the next level of analysis. Now, as you can imagine, it's probably really, really hard to see shadows, first of all, let alone to see the different polarizations of the molecules that are in their atmosphere. And so, the better our instrumentation gets, the better chance we'll have of seeing these kind of things. This is just an example of this. Let's see, what do I want to say about this? Another thing I guess is worth mentioning is that life turns out to like these really light isotopes of chemical elements. So what does that mean? Well, chemical elements, atoms, they don't all have the same weight, right? In other words, they don't all actuate the same level of gravity and inertia. Some of them seem to have more than others, and it has a lot to do at an accounting level with this thing called the neutron. And so atoms that have more of these neutron, they have more material on them, let's say, they have more weight. And atoms tend to be, let's say, if you look at across the periodic table, each one of these different elements seems to be a blend of different weights different. It's not a homogeneous category for each element. And so we can look and we can see the spectroscopy. We can see the light that each one of these elements produces, in particular hydrogen, which is the most abundant element. We can see from its light which it is, whether it's the heavy kind or the light kind. And we know, again, that life tends to prefer the lighter kind, and so that's probably something we can keep an eye on. But there's a bunch of these little molecular signatures, and again, when you're looking for molecular signatures, you're really looking at the light that's coming from these different molecules. Remember, all atoms, this is a very good rule to remember in general. So anything that can take up light can also give off light. In fact, they're in proportion to one another. So if you absorb light at a particular frequency, you also give it off at that same frequency if you have enough energy, let's say, if you're an atom or a molecule. And so each one of these chemicals that we see up here, they each have their own little fingerprint of frequencies of light that they give off, right? And this is kind of a cool table. I think it's worth kind of picking this apart a little bit. So what you want to do when you start thinking about a habitable world is you want to start thinking about things that you don't want to see, which is down on the bottom here, and you want to start thinking about things that you do want to see. Of course, the things we do want to see are the things that are naturally occurring on Earth. In particular, water and oxygen and things like that. Now, carbon monoxide, why would we not want to see that? Well, the funny thing about carbon monoxide is it also is extremely polar, right? And what it'll do, since it's a dissolved gas in the atmosphere, is that it'll bind to your red blood cells, let's say, much better than oxygen will. And that's bad, because that means that your body can't get oxygen, which means it can't breathe. And so carbon monoxide, of course, will kill you, and we don't expect to see an abundance of carbon monoxide on Earth. Well, obviously not on Earth, so we wouldn't want to see that everywhere. And so, what else? Some of these other molecules, like these tetraoxygen compounds and so forth, they kind of can give us information about how much oxygen is on a planet. So if you have a ton of oxygen, like something in the neighborhood of the 20% that we like, you actually start to see the production of these multiple oxygen species. So that's a really cool thing to keep an eye out for. But in general, there's this span of possibilities for what we want, and there's a span of possibilities for what we don't. And we can start to, I don't think that this work has really been done too much at this point, but this is the thought process for how we should go about processing this data in the future. The problem is it's just really, really hard to get these light signatures from these exoplanets at this point. The best resolution that we have, to my knowledge, is really showing that yes, there's water there, there's not water there. Maybe we can see some information about the isotopes and chirality, but it's a little bit of a futuristic thinking that we'll be able to detail these processes. Sometimes we get lucky. Sometimes there's a big planet that passes in front of a really bright star, and we can get really nice spectroscopy off the atmosphere. So there's a few of those, but it's not totally robust yet. This is a little bit futuristic. There's also this problem that some of these biological molecules, we didn't even talk about that, but there's also molecules that are just, we tend to think of as just being made by biological organisms, right? So, when I was a kid, they called oil, for the most part, they called it fossil fuels, right? It kind of stopped doing that in the last 10 years. I guess some people still do it, but it's become overwhelmingly clear that these fossil fuels, particularly methane and things like that, they're found throughout the solar system on other planets, right, that clearly don't have life on them. And so there seems to be an abiotic way of producing these hydrocarbons that has nothing to do with life. And so that's one of the ways we can get tripped up, is if we start, originally it was thought, okay, we'll look for these biomolecules, these hydrocarbons, and if we see them, we'll think maybe there's life there. But there's a number of ways in which these things can be produced that have nothing to do with life. And so there's the possibility of red herrings along the way too, which can become a bit tricky. All right, so let's say that we actually get out, well, we've gone to Mars, let's say we've gone to the moon. Would we be able to see some record of there having been life there in the past? That's kind of the hope in some sense as well, which, that seems a little less interesting to me personally, because if there was in the past, I mean, there isn't anymore. I don't know that it's very useful to us, but there's some hope that we'd be able to see these microfossils. So this is actually a microfossil from a deep core sediment from the deep sea drilling program. And that's about 2 microns, right? So you can think of a bacteria as maybe about a micron long. So these are little organisms that are found down deep in the crust. And they're, on the order of maybe like 5, 10 bacteria long, little animals basically. So there's some sense that we might be able to comb through, and it's a fossil, right? I think that we got the impression before of how, I don't know if you realize this, but like fossils are extremely difficult to find, right? You can have sometimes billions of years with no fossils. You can have at least millions of years with no fossils, because something dies, it decays very quickly. You need the exact right ratio of acid and base chemistry in the soil. You need to have it be coated at the right time, in the right season, in the right latitude, and so forth. So it's very difficult to make fossils. So anyways, this, I think your textbook mentions this, but I don't have a lot of hopes pinned on that. Now, here's where things start to get really fun. What about finding life that's like us, that's intelligent and communicative, and so forth? And this is what gets a lot of attention these days, I feel like. And it's a valid line of exploration, I think. So what these are called is technosignatures. This picture here is actually from SETI, which is the Search for Extraterrestrial Intelligence, which is a alternately very highly funded and very underfunded program, a research program run out of the United States, that essentially scans the sky for any sort of radio signals that we might receive from other worlds. And it's interesting, this picture they have here. Does anybody know what that is? The idea is something like, this is called a Dyson sphere, actually. And the idea is that if a super technical, it's funny because I think a lot of times when people imagine aliens, they're really imagining us in the future. But what they imagine is that the aliens, if they were resourceful enough, would eventually find a way to harness all the power from their star, right? Because, all of our energy comes from the sun, essentially. There's a little bit of heat under our feet, but not very easily accessible. So, well, how do you maximize that? Well, the idea is that the aliens would build a big shell around the sun, essentially, so they could catch all of the radiation and heat and light from the star and power their civilization. And so, there's been, we talked about Betelgeuse a while back, right? Which was this variable star that's in the Orion Nebula. You can see it in the night sky pretty easily. And it's alternately dimming and brightening. And there was a number of speculations going around during one of the most recent dimmings about, well, maybe it's one of these Dyson spheres that the aliens have put up around it. Which is pretty far-fetched, but, crazier things have happened. So technosignatures, that's really interesting. By the way, SETI is kind of broke right now. If you want to help them out, you can sign on, you can log on and help crowdfund them by donating part of your computer to their processing of their data. So I thought I'd give them a little plug just now if you want to get involved in that. Because obviously there's massive amounts of data and somebody has to comb through it all. And they're using, of course, artificial intelligence algorithms for that, but it requires processing power. But it's not a very, this technosignature thing seems to be getting a lot less interest these days than the basic biosignatures that we were talking about. And yeah, I'll open up I want to hear what you guys think about why that is. But previously, actually, SETI had one interesting signal in all of the, 30, 40, 50 years that it's been operating. And this is that signal. The guy who recorded it wrote wow next to it. So it's called the wow signal, which is quite interesting. It was just this narrowband radio signal detection that was like a non-random signal, right? It was some repeating pattern that didn't seem like it made sense. The problem was that this signal lasted for, I guess, 72 seconds. But they never ever were able to find it again after that. They weren't able to re-record it or study it or anything like that, so people just kind of forgot about it and moved on. But tantalizing, perhaps, maybe something going on there. We also are doing our part. This is a picture of the plaque that was slapped onto Pioneer 10, which was this, essentially a satellite-looking spacecraft that we just threw out outside of our solar system. And it's an interesting calling card that was designed in some sense to tell the aliens, if they're out there, who we are. Which might not be a good idea, I don't know. I mean, we've actually drawn a map here. This is supposed to be a map to various stars to sort of tell them where we're at, which, hopefully they're friendly. I'm not sure. We also sent them some naked pictures of ourselves, which I don't know if they'll appreciate or not. The female is not anatomically correct, which is going to be very confusing to them, I think. So it's a very strange, that was a strange project. There's also some records with music on them, which, that's a nice calling card, I suppose. Maybe just leave the naked people on the map off the next time. So the question becomes, why don't we see anything, right? Does anybody have any ideas? Like, why aren't we seeing any aliens? I mean, either they're really, yeah. Do you have an idea?
My idea was just that it seems like we're pretty rare. Like our solar system is pretty unique. If life outside our solar system is anything like us, I would imagine that it would also be extraordinarily rare to find probably in this galaxy.
Yeah, so I think that's really what it comes down to, is a numbers game in some sense, that life itself seems to be really rare. There's not a lot of it in our solar system. In fact, this is the only life we know of, is the stuff on our planet. And then among the organisms on our planet, there's only one that's really sending rockets into space and broadcasting radio signals, right? And I don't even know how many life forms there are on this planet, but gazillions. And so it seems like that by itself, even in this time period, is extremely rare. Now, you talk about billions and billions and billions of years progressing. I mean, how long? Hopefully this civilization keeps going forever. I love it here. I want to see it take off. But, what's the odds that a civilization can persist at this level of technological progress without inundating itself? We've had several close calls in recent times, right? The fact that we have nuclear weapons capable of destroying every single life form on this planet, I mean, we possess that ability right now. What are the odds that a civilization gets past that point and doesn't destroy one another? It's a good question. What are the odds that it doesn't get leveled by a meteor before it figures out a way to get to another planet? Like I said, we are a long ways off from being able to colonize another world, let alone just find another world that's worth colonizing, let alone figuring out how to get there, right? This could take 1,000 years from now, even if we find a place we want to go to, just to figure out how to travel such extraordinarily astronomical distances. So, yeah, the odds are kind of stacked against life persisting for any particular length of time. So it's possible that something like human beings could arise at some point on another planet, it's possible inside of our galaxy. But maybe that happened, 1 billion years ago, and it lasted for, even being generous, it lasted for 100,000 years. Well, that's almost no time in the course of 1 billion years, right? This is just such a short window. And the idea of us surviving for 100,000 years is something of a pipe dream still today, right? It's hard to imagine. I mean, we're 300 years into technological civilization, right? I mean, since we started playing with engines, let's say, and industrial agriculture, things like this. This has really been, that's generous, like 200 years, industrial agriculture. Engines, electricity, little more than 100 years we've had electricity, right? Can people do that for 100,000 years? Can they do it long enough for us to even see them? And so that's kind of the line of thinking about why we haven't seen any technological civilizations and why we're probably not in danger of getting attacked by aliens anytime soon. This guy, I can't remember his first name. His last name is Drake. famous scientist, he concocted this equation that kind of lays out the different variables here. And essentially, it's just a probability list. It's sort of like we take the odds of this happening times the odds of this happening times the odds of this happening, and we try to figure out how many worlds we would expect there to be at any given time in our galaxy. And if you look at some of these variables, how many are even out there in the galaxy at any given time? What about the rate of star formation? Remember, if the stars are being formed too fast or too slow, that can absolutely devastate a civilization. You get supernova and all sorts of things. Fraction of those stars that even have planets, the number of Earth-sized worlds per planetary system. The number of communicative civilizations is the number we're working towards. These are all the factors. Fraction of those Earth-sized planets where life actually develops, fraction of life sites where intelligence develops, fraction of communicative planets, so those who actually have figured out radio waves and electricity, and then the biggest one that I've been kind of harping on is the lifetime of those communicative civilizations. So how long are they actually putting their messages out there? So that's a lot of factors that kind of fights against anything persisting. It's funny, every single radio wave, light dissipates very quickly, right, with an inverse square law, and radio waves are no exception. But we have been sending radio waves out into space ever since we started radio, right? And I think some of the first really big global broadcasts were not something that we're going to be super proud of for our aliens, because I think they were done by the Nazis for the most part. So we're going to see, I think the aliens, the first signal they're going to get from us is Hitler up on a podium saying something perverse. It's not going to be a good look. So that's really interesting, though. We should be able to receive radio signals from places should they be producing them still. And yeah, nobody's seeing anything except for that wow signal. So yeah, I don't know. Intelligent civilizations, if they exist, maybe, there's also the possibility maybe they don't want us to see them. That's a totally reasonable, I kind of made the joke, like, why are we telling the aliens where we live? But I don't think I'm alone in that. I think there was a lot of pushback after that Pioneer plaque that was like, hey, wait a second, do we really want people to see us? I actually think that if we were, I think it's almost inevitable that at some point, if we have the ability to hide our location from everybody, we would probably do it, right? Just as a precaution. I don't think that you would really want to be broadcasting your location to potentially hostile other people. And so I think that there's also a missing variable here, which is like, maybe the aliens don't want you to see them, right? So it's very possible that they're not broadcasting, their Hitler messages to us because they don't want us to hear them. And so they've been more careful than us about putting out those sort of, light pollution, for lack of a better word. All right. I think that I've said enough about life and our quest for persistence. In some sense, our goal as a species is to persist, and we're going to have to. And I feel like the Earth almost made us for this job, right? It's very interesting. If you look at the traces of the humans as we branch out through the solar system, it's almost like we're little tentacles reaching out from this planet. And so it seems like this is part of our job as a species, which is pretty cool. Anybody have any thoughts or questions about the search for life before we move on to something more geophysical? We're going to start talking about the moons and Mercury next. Questions? Thoughts? All right. Let's start talking about the moon, and we'll finish it up next time. This kind of ties into what we're doing because, of course, the reason we care so much about the moon. Well, there's probably lots of reasons we care about the moon, but a huge part of that project is that it's nearby. It gives us a chance to practice our space exploration techniques. And in some sense, that space exploration project, I really firmly believe, is about us finding a new home. And so everything we're going to be talking about with the history of the exploration of the moon, and really what's kind of cool is that it's going on right now. So we've just started a new program to essentially get back to the moon, because the idea is we visited it once back in the 1970s and then kind of gave up, threw in the towel for 50 years because Well, that's a good question why we gave up on it. But it wasn't that expensive too, so it's hard to understand why we stopped doing it. But I think part of the reason we did it in the first place is because we were competing with the Soviets during the Cold War, and we kind of wanted to show them who's boss or something like that. So that's happening again right now, and we're back to exploring the moon, and there's a lot of ambition about setting up bases there, potentially eventually making it a spaceport for further exploration. And I think that's all pretty exciting stuff. But I think we need to start with asking some basic questions about this moon, like what is it, what's it made out of? It's a very interesting body in that it's so close to us. It's been the one that people have been able to actually examine for the longest. I think if any of you have ever, I don't know if you own telescopes maybe, or one of your friends has or something, it's the easiest thing to look at in the sky, right? You can actually see all of the little features and craters on it. This is, of course, the moon, both sides of the moon. I hate to break it to you, there's no actual dark side of the moon. Sorry, Pink Floyd. Just from our perspective. Now, of course, the moon, one face of it is permanently locked to facing us at all times, right? So, in so much as the moon is rotating with respect to all the other bodies in the solar system, it does not rotate with respect to us. And so the same side faces us all the time. I think this is the idea of the dark side of the moon. But in reality, it's getting illuminated by the sun, just as we've shown in the phases of the moon at the beginning of this course. So the moon has these interesting features. It has these craters, and it has these big dark spots that are called maria, which is, the root of that stems to seas, because people originally thought when they were looking at it that these were giant oceans. They're not. The moon is actually, all but devoid of anything useful to life. There's very little water. If there is water, even it's at the poles, under the surface, and some ice. There's very, very little atmosphere, almost none, let's say, for all intents and purposes. And for most of human history, people thought that these craters were actually volcanoes, which is really interesting. It was only very recently that people determined that they were impact craters. Now, what's interesting is that why didn't they think they were impact craters? Anybody? Because they never saw the moon get hit by anything, which is crazy, actually, if you think about it. So look at this. This is gonna. I want to remind you guys of a famous quote from Richard Feynman, who's one of the OGs of physics, let's say. And Feynman said that science should be the discipline of skepticism, and religion is the discipline of faith, right? And so you always need to ask questions when things don't make sense. And one of the ways that people originally thought that they could come up with the age of the moon was by looking at the rate of crater formation on it. If there's a crater that happens this many years, every so often, right, you can clock things based on that, and we can kind of deduce, based on counting the craters, how old this thing is. The problem with that method is that it yields an age for the moon, which is something like 40 billion years old, okay? And of course, that doesn't jive with the idea that the Earth itself is only, say, 4.5 billion years old, which is based on this radiocarbon dating process we've talked about. So, it took a while to win people over to the idea that these were craters and not volcanoes. And of course, when we visited it in the 70s, it became absolutely abundantly clear that they were not volcanoes. However, these giant flat regions, these maria, seem to be this basaltic rock that you would associate with volcanoes here on Earth. And so it's thought that they are from some giant melt in the past, something approximating a giant volcanic period on the moon. So some interesting mysteries there, honestly, particularly with the dating. I mean, it's possible. I think that well, we'll get into that more. I have some charts to show you, but the common consensus now is something like, well, there was a lot of impacts at one point in the future. Almost all of them happened, let's say, one geologic day out of the year in terms of the lifetime of the moon, a long time ago, and it just doesn't get hit that often anymore. Which maybe. What do we know about the moon's interior? Not too much. We know that it has a pretty, let's say, dormant interior compared to Earth. It's molten regions, right? It has a solid inner core. It has a little bit of a molten region outside of that, but it's rather small compared to our own. You might ask, how in the world would you know that? It's the same way that we know about our own interior, which is by doing these, essentially examining little moonquakes, right? And seeing the echo of those sound waves as they travel through the moon. So they set up these sensors, and they're able to, well, they can actually do it with lasers. They can detect these tiny vibrations in the surface of the moon. They can get the frequency of those and deconvolve it and actually reconstruct the interior, which is a highly technical process. But, you know, for what it's worth, I think it does give us some really interesting information. So this thing seems like it's kind of cold and old and nothing like our Earth in that sense. It's not active like our Earth, which again is rather puzzling because the most popular idea for where the moon came from at the moment, which is brand new actually in the last 10 years, is that it was formed during a collision by a different planet that no longer exists with the Earth some 3 billion years ago or something like that, which completely liquefied the surface of the Earth and of course liquefied the moon and so forth. But you know, as to why it doesn't have the same level of interior warmth is a bit perplexing given that narrative. Now, the cool thing about the moon, of course, is that we can go there, at least in theory. I mean, we've been there in the past. We can, in theory, go there in the future. We've started that process, but people have been dreaming of going to the moon since ever, essentially. There's this really, really funny movie that I recommend you guys all watch called Les Voyages dans la Luna, which is, it's just a very funny film, and people imagine, of course, that they're going to wear their top hats and fly off to the moon and so forth. And you know, actually, the rocket that they take isn't that different looking than the one that we ended up doing. Actually, the serious idea of going to the moon wasn't proposed until the 1920s by Robert Goddard, who was a rocket scientist at the time. The Goddard Space Institute, which is NASA's science wing, is named after Goddard at this point. And so almost everything that we know about the moon today is derived from the US Apollo program, and to some extent the Soviet Luna program. All right, it's like we out of time. Which is interesting because that means that everything we know about the moon, it comes from the last 50 years. I mean, we had some idea of the rough surface features and so forth, but all the technical information about its composition and so forth comes from very recently. And, you know, we've only put 12 people on the surface of the moon ever, which is interesting that so much information would come from so few excursions. The story of how those astronauts got onto the moon is actually really fascinating too, because, you know, if you think about it, they pulled that off in a very short amount of time. Let's say between the rockets first appeared in World War II. Britain was getting pummeled by these V-2 rockets from Germany, right? This was a real nightmare, and nobody else had rockets of that sort. These kind of precursors to intercontinental ballistic missiles. They basically shoot these things up high in the atmosphere and aim them, drive them towards some target, right? This is how rockets science came about, actually. What you might not realize is that, well, you probably realize that the Allies conquered the Axis powers in 1945 and captured Berlin. What you might not realize is that they actually sort of swooped up all of those Nazi rocket scientists and dragged them back to the United States to build our space program. So there is a really, really interesting, rich history of how they went about capturing all of these Nazi scientists and dragging them back to the States, because it wasn't an easy thing to do. As you can imagine, all of these Nazi scientists were very afraid for their lives, and they were way ahead of the Allies in terms of their technical powers. They had jet engines and they had these rocket devices, and the US and its allies were nowhere close to having anything like that. So they actually had to send all these agents out into the field to scoop up all of these plans, and the Nazis were also working on a nuclear project at the time. They wanted to steal all that information up. But what's really interesting is that basically the individuals that built our Apollo program here, which was successfully launched in the 1970s, they were all Nazi scientists that we captured and brought back here. Interesting little known fact. So, yeah, spoils of war. It's a really, really interesting sort of dark undercurrent to space progress in general. And what's really, I mean, you see this everywhere. It seems like a lot of technological progress is in some sense first actualized in military development. A lot of, like, all of our basic computers, right? This basic technology was developed for military applications first and foremost. All these communications, your cell phones, all that stuff was contracted by the military originally. And then, you know, when there's no wars to fight, then the commercial sector gets a hold of the plans and they start making products for the rest of us. So, yeah, war is a really interesting conundrum because in some sense it does give a lot of technological progress, but at what cost kind of thing, you know? Okay. The Russians made it there first. They had their version of the Apollo program was called the Luna program. Luna 3 was their third attempt at this, and they were actually able to, let's say, orbit the moon and return a picture of its far side. That was in 1959. So that's about 14 years after the end of World War II, which is pretty incredible. I mean, as soon as they brought these V2 rockets back to the United States, they started trying to launch them out into outer space. And one of the first successes, I think within 5 years or so after the end of the war, was they were able to take a picture of the Earth for the first time, which is pretty remarkable. Nobody had ever done that before. So they launched one of these V2 rockets. They started calling them Saturn rockets. And they launched it up, and they took a picture from like 100 miles above the Earth. And that was one of the first features. But the Russians were working on it too. And so the Russians transmitted this picture, not this picture. Their picture was probably pretty crummy. I didn't put it in here. Then they also managed to land a robotic module on the surface in '66 and send some pictures and other interesting data about the atmosphere and lack thereof and the soil and so forth back. That was in '66. And then, of course, kind of out of nowhere, the U.S. really was trying to keep this under wraps. The U.S. actually just put a person down on the moon in 1969. And they did that for a little while. Here's a list of the Apollo missions. All in all, there was, I guess, 17 of them. Not all of them actually landed on the moon. And they had varying degrees of success. Now, I don't know if you guys, there's a kind of cool Hollywood film about the 13th mission, which was a bit of a disaster and almost went awry. I think that around that time, it seemed like it was potentially a more dangerous endeavor than it was yielding any sorts of fruits that the American public could get behind. And so it sort of lost favor. This was, of course, also happening right around like the height of the Vietnam War. So the government kind of had its hands full a little bit. There was a very, very unpopular war towards the end. So you can see a number of missions, and then essentially we just stopped going there all of a sudden. Which is, a really, I think in some sense, why did we stop going there? It's like, I'm not sure that people had an idea of what to do next exactly, right? It wasn't clear, well, why are we doing this? Why are we wasting all of this time and energy going there? The funny thing is that it doesn't seem like it was a particularly expensive endeavor. I heard a statistic somewhere. Here we go. To get people on the moon, it costs something like $100 per American spread over 10 years, which is something like, each person buying a pizza every year to make this project happen. So it wasn't that expensive. The only thing I can think of is that they just didn't really know what the end game of it was. What are we actually trying to do here? And I think that it took the next 50 years for people to actually consider some of these problems. Remember, like guys, I told you last time, nobody even cared about asteroid impacts until the 1990s when they saw that Shoemaker-Levy explosion on Jupiter. They didn't know about the Yucatan crater until the 2000s, actually. That hypothesis for what killed off the dinosaurs wasn't really seriously entertained until, after I was in college, basically, which is crazy. So these are like really new ideas that came about, and I think the existential threat of things coming for us from outer space has really reinvigorated the project of exploring. And obviously the moon makes a really good test case for how we can pull that off. All right, the Soviets kept doing that, by the way. I don't know if there's much to say about them. The Chinese are also working really hard right now. This is the last, let's say, 20-ish years of people who are working out there. There's various orbiters, landers, rovers, robotics. I think even, who else do we have here? China, US, Japan, the UAE is out there. It's very interesting. It's clearly shaping up to be the next big industrial market in some sense. Because look, as I've said before, every single industrial process you can think of doing on Earth, you can do like 10 times cheaper on the moon. That's what it comes down to. There's no, the vacuum is easily achievable. There's no, issues with assembly. You can send things into orbit really cheaply. You don't have to worry about the atmosphere getting in your way. And so it's clearly lining up to be a fruitful endeavor for people. So everybody's lining up to get out there right now. The USA, Russia, China, Europe, Israel, India, Japan, South Korea, everybody is planning lunar missions right now. Now, this is the big one that's going on right now. Let's see. Okay, this is the big one, which is interesting. So this is called the Artemis mission, which is interesting because we talked about Artemis when we were talking about the story of the big bear in the sky before. And it's just so interesting to me how these myths, we just can't let go of them. They're just somehow extremely important to us. And so this project has been named the Artemis Project. What's really interesting is that the Artemis Project is making use of a rocket which isn't so extraordinarily different from the Saturn rocket, which isn't so extraordinarily different from the V2 rockets from World War II. Basic same floor plan, at least, that you have this fuel. Most of the thing is a fuel tank, and you just kind of light it on fire and shoot it out the back and get yourself up into space. So the end game of the Artemis mission is to not only put people back on the moon, but also to eventually set up like a permanent base there, which is really interesting, replete with a little bus to drive the people around so they can go and explore, hopefully get down to that South Pole, right, and figure out where this water supply is located at. It's very similar in the Apollo mission in that there's an orbiting module and there's a landing module. There's different stages of the craft that depart as it goes through its role. And this is kind of the end dream, right? You have a little permanent base set up. You got a little minivan type thing, and you have crew that's kind of permanently stationed there and going back and forth. So let's go through the phases of this. The first phase, which actually went down last year quite successfully, Artemis 1, was essentially a test flight. So they launched an uncrewed version of this module, which did a number of things. It circled the moon, and it kind of came back, something like that, and delivered the crewed module at the end back to Earth, which is good because we obviously want to get people back here. The next version up is going to be, let's see, they're going to actually put some people in it, right? This is supposed to go down and this is supposed to go down in 2024, so next year. And the idea is that people aren't going to actually land on the surface this time. They're just going to go along for the ride. So the idea is now that we've shown we can do the spacecraft, we can return the spacecraft without anything bad going on. Now we're going to put some people in the spacecraft, send them on the circuit, and then the final stage is, of course, going to be doing the same thing, except we're going to land the people on the surface of the moon again for the first time in, what will have been nearly 60 years at that point, using essentially an updated version of the very same technology that we used half a century ago, which is just really, really fascinating that the basic plan has remained intact since the beginning. All right. You know, a lot of the space visionaries in the private sector are also extremely ambitious about this, right? There's so Elon Musk and Jeff Bezos are also planning something in parallel. They want to do the same thing, except they want to sell tickets, right? Which is, you know, people are lining up actually to buy these tickets. There's people who've bought these tickets already. People, you know, space tourism is like a legitimate enterprise at this point. People are spending millions and millions, tens of millions of dollars to buy tickets to go on these spacecraft up to space, as it is just into orbit. Imagine what they'll pay to get out into, to get to the moon and hang out. I mean, it's interesting though, because you can imagine a situation where you know, everything is really, really expensive at first, right? It's like, I remember when CD burners first came out, and like, man, they were like $5,000, well, 1990s dollars, right? Like $10,000 in today's money. And I knew a couple people who had them, and it was just like, wow, this is incredible, you know? Because you have to pay $20 for a CD back then. And but you know, within like 5 or 10 years, every single computer had a CD burner in it, and they were like modular parts that cost like $20 to insert into your computer. So I don't know. It's like maybe the billionaires lead the way with this stuff, and then maybe at some point anybody can just take a ride to the moon anytime they want. It's like jumping on an airplane at some point. The cool thing, like, I guess I want to talk about in detail, maybe with the last few minutes here, about what makes the moon such an attractive place. Because obviously it's a barren hellscape. It's not going to be fun to like take your dog for a walk on the moon or anything. But it seems to be really industrially attractive. And I want to just make sure that you guys understand that before you walk out of here. So the cool thing is, the idea is not that we take a bunch of metals and, you know, plastics and everything out to the moon in order to construct all of the moon bases. The idea is that we build all of those things on the moon for all of our space projects in the future. So everything we need is there. This lunar regolith has, that's the rock that the surface of the moon is made out of. It has everything we need to be able to fabricate things. That's the dream, and it seems promising enough that people are putting their money on the line to make it happen. So you don't take things with you to build them on the moon. You build them out of the stuff that's on the moon. And that turns out to be really, really cheap, because construction's really, really cheap there. You can assemble these giant spacecraft. I don't know if you guys remember last week, we were talking about the idea of sending a whole biosphere to another star system, right? Because that's probably what you'd have to do. It's going to take you 100 years to get to the nearest star system, going very, very fast. And so how do you make something that big? Well, it's extraordinarily expensive to put even something the size of a trash can in space today, right? It can cost millions of dollars to put a satellite in space. But on the moon, it's really cheap, actually. You can literally throw things up into the sky hard enough, and they just go there. There's no atmosphere to hold you back, which is really nice. And gravity is, I think it's something like 1/6 of the gravity on the moon as it is on Earth. So it's just very, very easy to get things in orbit where you can assemble the things as they're orbiting around. So there's this tool that they actually imagine using for this, which is cool too. You don't actually, like I was saying, you can throw things in orbit. They have these things called railguns, where they actually, or they call them mass drivers, but it's essentially just a slingshot type thing, where you basically just spin something around and let it go. You use that inertial acceleration, just like our good old figure skater. And you sort of just, or like, what is this? The shot putters do this kind of thing. Discus throwers, you spin something around and you just launch it up into space. This turns out to be way, way cheaper, because you don't need fuel to do it all of a sudden. You can just charge up your solar panels, get a good electrical battery going, and you can just fling these things up into orbit without actually having to burn anything. And that turns out to be really, really cost effective. So the moon's a great place to assemble stuff. Turns out there's also a number of these different markets that have actually opened up already on the moon. This is kind of funny. I mean, there's everything from hospitality to communication people to R&D, like all of these industries that you see on Earth, right? I mean, literally, like hotel chains are interested in this, right? This is like all of these different niches are getting on board. And so space branding, like that's a thing. Like some marketing company is already trying to sell branding solutions to these moon companies, right? So it's a new market, and new markets often tend to be flooded with resources. There's also all these different elements that are kind of rare and useful. You guys have probably heard that, our cell phones contain these rare elements that are really, really costly and deadly. Like you have to mine these out of these terrible, terrible places in the Congo, right? And there's all this slave labor that goes into these. But those same elements are available on the moon. And the idea is that it could be done robotically. It could be done a lot cleaner. Of course, there's terrible, terrible waste when you tear up the landscape in the Congo and you pollute the rivers, and it's just a terrible, terrible situation. So there's lots of aluminum, calcium oxide, iron oxide, magnesia, titanium, sodium oxide, all of these wonderful oxides, which of course have oxygen in them as well. So we can actually pull that oxygen off. We could use it for breathing. We can we basically can find everything we need out there, which is really wonderful. And then of course, the end game promise is that we'll be able to combine all of these with the water that we are able to mine from the poles, and essentially set ourselves up a very nice shop. So the next thing that I want to move towards when we start next time is I want to talk about Mercury, because Mercury looks a lot like the moon, it smells a lot like the moon, but it's in some sense very, very different from the moon. And so I want to compare and contrast those two bodies, and then we're going to work towards talking about the rest of the rocky planets as we go forward. But yeah, hope I gave you guys something to think about. I'll see you guys after the weekend. Yeah, have a good weekend.